Hello everyone, welcome to the IAL Unit 1 predictions for May 2026. And even though I have said this is the guide to grade A, this video alone is definitely not the guide to grade A. There are several other resources involved that I'll be sharing with you all. Um, if you follow all of those, then you might have a chance at grade A. I repeat, this video alone is not going to ensure, the best grade for you. What I've included in this description is the most frequently asked questions and answers of Unit 1. And when you download this, make sure to add the free definition sheet in the cart. Get it for free. Link is in the description, and let's get started. Like I said, this is not the only resource that you should depend on for your preparation for your exam tomorrow. I have made a full syllabus revision video for Unit 1. I will highly recommend you to go through that one as well. Now, so this is, you can say, crash course of sort of preparations, and this is what you can get started with, right? But make sure this is not the only thing that you end your preparation with. So there are three sections of Unit 1 in the broader scheme of things. One is mechanics, second is fluid mechanics, and three is solid materials. What I have done in this video is compiled a list of um, what I feel is the most important topics. I wouldn't say that is most likely. Of course, the most important ones are the most likely to appear in the exam tomorrow, but this is what I just felt myself. Okay, this is just my personal preference. I have no access to the script prior to the exams. So let's first look at the sections of mechanics. So very likely you'll get a projectile motion question. And to answer this question confidently, you should have a very clear idea about the three scenarios in projectile motion. So the moment you see the diagram in your exam paper, it should instantly pop up in your head which specific scenario are you dealing with, because every different scenario has a different feature and aspect to it. So the first scenario is where an object is launched and lands at the same height from which it is launched, meaning the total vertical displacement is zero. That is scenario one. And throughout the whole motion, the acceleration is minus 9.81. In scenario two, an object is launched from a height but horizontally. Since it's launched horizontally, it has no initial vertical motion and so no initial vertical velocity. But since it's moving in only one direction, the acceleration throughout the motion is just 9.81. Scenario 3 is the most interesting one. It's where an object is launched at an angle from a height, and you'll see the projectile lands below the point it is launched from, meaning the displacement, as in final displacement, is negative because it is below the point of origin. So another thing I need to discuss with all of you is you should have a very clear understanding of the origin, because in recent papers I'm saying there are a lot of questions where you need to identify where the origin is to draw a graph or sketch a graph properly and do calculations with it. And there is a whole video on projectile motion in my channel. You can refer to that. Also, I have discussed some very important topics in the full syllabus revision video as well. Next up, what I feel is most likely to appear in the exam tomorrow is a question with law of conservation of momentum. So in most questions, most papers, you'll see the law of conservation of momentum is applied in collisions, but explosions are also there in your syllabus, right? So when you apply total momentum before collision, equals to total momentum after collision. The same thing applies to explosions. Total momentum before explosion is equal to total momentum after explosion. For example, in this scenario, this object before it explodes uh, has a mass but doesn't have a velocity. It is at rest. So its momentum is zero. And after explosion, the fragments move in opposite directions to conserve momentum. And if you add up these momenta, momentum being a vector quantity, since they're in opposite directions, their momenta cancel each other out. Okay, so making the total momentum zero again. So this is how you apply law of conservation of momentum in explosions as well. And if the question comes with collision, there might be a section at the end where they ask you whether it's an elastic or an inelastic collision. Right. So when it comes to elastic or inelastic collisions, what you have to remember is you have to find out the total kinetic energy before and after. If the total kinetic energy before is equal to the total kinetic energy after, then and only then you can say that this is an elastic collision. Then very likely there will be a moments, as in principle of moments question. So let's look at a very simple scenario here, right? So this is a beam and the beam is in equilibrium because the total clockwise moment is equal to the total anti-clockwise moment. So in questions like this, they can directly ask you what do you mean by a body in equilibrium, right? So these questions are clearly answered in the definition sheet. Definition of equilibrium, definition of center of gravity, right? All of these are there in the definition sheet, also in the fact sheet. But what I want to show you in this video is how they can elevate a concept. Just look at a simple IGCSE level scenario like this, right? So what they can do using this is they can apply this in a specific context. So it is hung from this position and the dish and the rice is producing a clockwise moment and the weight acting from the center of gravity of the beam is producing an anti-clockwise moment. And since this is in equilibrium, again the same concept applies. Total clockwise moment equals to total anti-clockwise moment. Now, issue is somewhere else. When it comes to Unit 1, there are a lot of concepts that include and incorporate vectors in them, and moments is one of them. So look at this scenario. In this scenario, um, if I take moments about this point, because the question asked me to do that, what you do is look at the tension, right? So this tension is not creating the clockwise moment. It is basically the horizontal component of this tension. So the horizontal component, there is no angle here. So without angle is sine theta. That makes it T sine 44. And whenever you encounter questions with moments, always remember you have to consider the force and the perpendicular distance from the force to the pivot, perpendicular distance. So if I'm dealing with this force, I have to consider the perpendicular distance from this force to the pivot. This is the distance. So T sine 44 times 1.5 is basically the clockwise moment. And 25 times 1.8 because force and perpendicular distance. 25 times 1.8 gives you the anti-clockwise moment about this point. So you can find out T from here. You can actually pause the video and find out T. Okay, let me give you the answer. And I'm not going to show you how to do this because this is not a video for solving papers or solution of papers. This is a video uh, to show what you need to revise, right? So I'll pause the video and I'll write down the answer. You do the calculation and see if your answer matches with mine. So I hope you have done it. The value of T is 43.2 Newton. Another trend I'm noticing in the recent papers is they're bringing in concepts from M1. So this used to be a very common concept in Unit 1 as well, but it's been a while. They haven't introduced this question in the recent papers. So I thought I might just include this in the revision video. So what happens is the larger mass M accelerates downward and the smaller mass M accelerates upward. There is tension in the rope and they both have the same acceleration. So what happens is since it accelerates downward, the weight mg is greater than this tension T. And since this accelerates upward, its weight, small mg, is smaller than the tension. So for this, the larger mass, since mg is greater, mg minus T equals ma. And for the smaller one, T minus mg, because this tension is bringing this up, right? So T has to be greater. Minus mg equals to, since this is the small m, small ma. And a is the same for both because they're connected, so they'll have the same acceleration. There were several questions like this, but it's been a while. Pearson has stopped asking these questions. But this is still in M1, so that I just thought I should include this in the revision video. And I'll tell you why. Look at this one. This is a classic mechanics question, but this has become a staple question for Physics Unit 1 as well. So what happens is a box or a block slides down an inclined plane. Right? So when the block slides down an inclined plane, if there is friction, the whole scenario changes. And let's first assume there is no friction. Okay, if there is no friction, then the only force acting on it along the plane is mg sine theta. And guess what? This mg sine theta is the resultant force. And you know the equation for resultant force, that is ma. So mg sine theta equals to ma. From here you can find out the acceleration because the m's get cancelled out. But if you bring in friction, then the whole dynamic changes. Then mg sine theta, as in the component of weight down the plane, because this is the only force that is in the direction of the motion, minus this is the other force in the opposite direction of the motion, friction. Let's call this Fr, right? And now this is the resultant force, that is ma. So I hope you have figured out the two scenarios with friction and without friction. So there is a 50-50 chance of a scaled vector diagram appearing in the exam tomorrow. So because in all the recent papers they have asked a scale vector diagram question. So there is a high probability, there is a medium probability actually. So whenever it comes to scale vector diagrams, always remember the vectors must be arranged tip to tail. Okay, always tip to tail. And for this specific question, I want to show you a variant. Okay, so you can draw a vector parallelogram as well, because there are two ways of drawing this. Let me show you both. Instead of just saying, let me just show you. So a sailing boat is moving through the water. The force of the wind on the boat is 350 Newton towards the north. The force of water on the boat is 410 degree at an angle of 120 degree from the north. All right. Determine the magnitude and direction of the resultant force. So I need to find the resultant of these two forces. Fine. So always remember, vectors must be arranged tip to tail. This is 350 and I place the tail of 410 at the tip of 350 like this. This is 410. And guess what? The resultant cannot form a complete loop. If it formed a complete loop, it would appear as though the body is in equilibrium, right? So when a body is in equilibrium, then and only then all the vectors form a complete loop. And since there is a resultant, the resultant one must be in the opposite direction. So these two in the same direction, this is the resultant F. So like I said, you can do this two ways. So for the first scenario, what I did was I placed the tip, I placed the tail of 410 on the tip of 350. I can just do the reverse. What I can do is I can bring in the 410 and at the tip of 410 I can place 350. The tip of 410 I can place 350 like this. This is actually, let me take out 410 from inside so that it looks less clumsy. This is 410 and this is 350, and guess what? This is the resultant F, and it cannot form a complete loop. This will be in the opposite direction to the other two. And if you join these two, what you'll end up with is a vector parallelogram instead of a vector triangle. If you join these two like this, you'll end up with a vector parallelogram. So you have two options. And of course, you have to do the scaling. And it's imperative that you mention the scale you have chosen for drawing the scale vector diagram. So the next section is about Newton's laws of motion. And I'm a bit surprised to see that how Pearson has completely forgotten about Newton's first law. Okay, it's also referred to as the law of inertia. So all of these scenarios are associated with Newton's first law. Let's first look at the first scenario. Here you have a card, cup, and a coin. When you flick on the card flies away, but the coin remains where it is and drops directly below into the cup. So how this works is the force only acts on the card. The card does not exert any force on the coin because friction between card and coin is negligible. After the card flies away, now there is a resultant force on the coin vertically downward, so it accelerates vertically downward. And every time you bring in acceleration, you refer to Newton's second law. So you can say that this is a combination of Newton's first law and second law. So how first law? Because when the force acts on the card, only the card moves away. There is no force on the coin, so the coin remains horizontally at rest according to Newton's first law. Same thing goes with tricks like this. So you must have seen in TV series or videos, viral videos where the guy pulls down the tablecloth from under the cutlery, right? And the plates and everything remain where they are. So this is again a classic example of Newton's first law. Because the force acts only on the cloth exerts no force on the plate because friction between plate and cloth is negligible. So this is not a very common concept nowadays. What is common is this, everybody. Right, so here you can see a swimmer exerting a force on the wall to move forward. So as her feet exerts a force on the wall, according to Newton's third law, the wall exerts an equal and opposite force on the feet forward. There is a resultant force on her body or her feet forward, causing her to accelerate. You know what? The swimmer will only accelerate as long as she is in contact with the wall, because there is a resultant force only as long as she is in contact with the wall. So this is a combination of Newton's second law and third law. This is way more likely. Let's move on to the next section. Okay, so now we're talking. This is energy conservation. So I strongly believe there will be some questions either in section A or section B regarding conservation of energy or energy conservation. So here, this is a very simple scenario. Um, a block slides down an inclined plane. Okay, if the surface is not smooth, when the block starts off, it starts at a height, so it has gravitational potential energy. In an ideal world, this E graph would have been transferred to the kinetic energy at the bottom, but this is not an ideal world. What happens is there is friction, and as the block slides down, there is work done against friction. So if you subtract the work done against friction as in resistive forces, what you end up with after subtracting the work done is the value in the form of kinetic energy. So this is a classic example. And actually, you know what? You can go in reverse. There was actually a question where it was about a disk, right? So a disk was launched from the bottom and it rose to the top, and the exact same thing. At the bottom, it had kinetic energy. So this kinetic energy was not fully transferred to gravitational potential energy. On the way up, it had to do some work against friction. So going up, it's kinetic energy minus work done against friction, which is equal to the gravitational potential energy. So you can go both ways, going down or going up. Going down, you start off with gravitational potential energy. Going up, you start off with kinetic energy. Next, okay, so this concept has become a staple Unit 1 concept in recent papers. It started from Jan 22 from the pinball machine question. So the scenario is this box or block initially is pressed against this spring. Okay, so when the spring is compressed, it has elastic potential energy. Okay, when it decompresses, this elastic potential energy is transferred to two forms, since while it decompresses, it goes up, right? So this elastic potential energy is transferred to the gravitational potential energy as well as the kinetic energy. But in a lot of questions, they ignore this part. So a lot of times what they do is this elastic potential energy is directly transferred to the kinetic energy over here when the spring decompresses. So this small change in E graph is at times just ignored. So it's better not to ignore depending on the context of the question. And finally, in the third scenario, you have a car moving with a constant speed. If it has a constant speed, it has some kinetic energy. When the brakes are applied, hear me out. When the brakes are applied, the kinetic energy drops to zero because the speed drops down to zero. So where does the kinetic energy go? All of the kinetic energy is dissipated due to work done against resistive forces. Even more appropriate would be work done by the braking force. So if you want to write down an equation for this specific scenario, it should be kinetic energy is equal to work done. If you break this down, and if the mass and the velocity is given, it's half mv square equals to, you just recall the equation for work done is F times S, and this F is actually the braking force. So for the next question, I deliberately chose this because you need to understand some very specific situations. And previously, I also told you you have to have a very strong idea about this concept called origin, right? So let's look at this question. the displacement time graph for a skydiver between jumping from the aeroplane and opening his parachute is shown. So you see the displacement starts from zero. So here, what they have considered is the point of jumping has been considered to be the origin. And since you are landing below the point of origin, all the displacements are negative. Okay. And how do I put this? A simpler uh, graph for this would have been, which you already know, would have been like this. So this is displacement time like this, right? And the corresponding velocity time graph would have been the most common one that you already know, velocity time graph. The velocity becomes constant, as in the skydiver reaches terminal velocity. Here, it becomes a straight line. So the gradient of a straight line is constant. Gradient of displacement time graph gives velocity. So the velocity becomes constant, right? But what they have done here is they have given a downward sloping line, meaning all um, the gradient at any given point is negative. Downward sloping lines always have a negative gradient. And guess what? The gradient of displacement time graph gives me velocity. So all the velocities will be in the negative axis. And the graph that they expected you to draw is not in the positive axis because a downward sloping line always has a negative gradient. And this is the graph that was expected from you for this paper. Up to 20 something. So I have to extend this line and go all the way up to 20 something. Yeah, something like this. So these are all new stuff, not previously asked ever. So you need to be wary of these concepts as well. Always look for the origin. And another example that I already discussed in my full syllabus revision video is from June 23, where uh, diver jumps from a platform. That's where the water surface was considered to be the origin. Any point can be considered to be the origin, by the way. Let's move on to the next section, that is fluids. So I just have a gut feeling that this paper might have something to do with mm, when an object floats or whether an object will float or not. So in this scenario, since this wooden block is floating, of course the forces on it are balanced. What are the two forces? One is of course its weight. The other one is the upthrust, right? But every time you come across upthrust, you just recall the definition of upthrust. It is the weight of fluid displaced. Okay, upthrust is the weight of fluid displaced, and you can see how much fluid has this block displaced. It is equivalent to the volume of the block that is underwater. So this is the volume of the block that is underwater, and this is the volume that will correspond to the thrust. Then this is a very straightforward concept. This might appear in your exam regarding Stokes' law. Sometimes they ask you whether Stokes' law is applied or not, or whether Stokes' law is applicable. So in questions like this, all you have to do is find out Stokes' law force using F equals 6 pi eta RP, and then separately find out the drag force using, if it's a falling ball, and always remember to draw a diagram. Questions like this. If it's a falling spear, the forces acting on it would be its weight, upward will be upthrust, and drag. And if it is falling with terminal velocity, all the upward forces must be equal to all the downward forces. So in this situation, weight should be equal to upthrust plus drag. And from here you find out drag separately and you just compare if the Stokes law force is equal to drag force. If they are, then and only then you say Stokes law is applied. And the other most common question is, what are the conditions for Stokes law? So the conditions are: the speed must be low, fluid flow around it must be laminar, and it must be small. And also remember, in Unit 1, every time you come across a question associated with temperature, you directly link it with viscosity, because temperature is always associated with viscosity. Now let's move on to solid material section. Um, in the most recent paper, that is Jan 26, you had to find out the combined spring constant. So this is a very good time to just review the whole concept. So let's say if you have just one spring, you of spring constant K, and if you add another identical spring with it in series, what happens is the spring constant halves. And conversely, if you add another spring with the one in parallel, the spring constant is doubled. And I can refer to you a question from October 2020, question 16C. Actually, this is the question. So the springs were identical to the spring used in the original investigation. Explain why the spring constant for this arrangement of the springs would half. Like I just said, if you connect them in series, the spring constant halves. The reason is same force acts through both springs. Each spring has the same extension, but the extension of the combination is doubled. The force remains the same, so F equals Kx. F remains the same, but since you are connecting both in series and each spring extends by the same amount, the extension of the combination is doubled. Guess what? K will be halved. The exact reverse thing happens when you connect them in parallel. Also, remember how energy changes. Okay, this can be a MCQ question or in a section B question as well. Okay, how the energy stored in the spring changes when you connect them in series and when you connect them in parallel, compared to when you connect them in parallel. Let's move to the next one. Okay, so this used to be a very common question. It's been a while they haven't asked this, so I just had a gut feeling this might appear in the exam. If it doesn't, no worries. I'll show things around this that will be definitely beneficial for your exam tomorrow. So you have a force extension, weight extension as in force extension graph. How do you find out the Young modulus from the force extension graph, right? So if you recall the equation for Young modulus, so this breakdown will be really important. Check this out. So Young modulus is basically stress by strain. Do one more breakdown. Stress is force per unit area divided by strain is extension by original length. So Young modulus equals F by A times, this will get reversed, L by del X. Now you do a flip, as in position swap. Bring del X over here and A over here. So Young modulus equals F by del X times L by A. Guess what? Force by extension is basically the gradient of the force extension graph. So what you do is find out the gradient of this graph and multiply the gradient with L by A, as in length divided by cross-sectional area, and you'll get the Young modulus. So this is a variant. And a simpler way to directly find out the Young modulus is from a stress-strain graph. But there is an exception. If your stress-strain graph is curved, you have to find out the gradient from the straight section, initial straight section from the origin. So you have to draw a tangent over here and keep on moving this as long as it is aligned with your graph like this. Yeah. And then you find out the gradient of this line. The gradient of the stress strain graph directly gives you the Young modulus. All right. So now that we have covered what does the gradient of the graph give us, let's now find out what does the area under the stress strain graph give us. So let's just assume up to the proportionality limit. Okay. So the area is, if it's a straight line, it should be the area of a triangle. So area of a triangle is half base into height, as in half into stress into strain. So area would be half stress is force per unit area, strain is extension by original length. Now I want you all to separate this in your head. What is half Fx and what is AL? So if the sample is in the form of a wire, which is basically a cylinder. So this is the cross-sectional area and this is the length. And area times cross-sectional area times length gives you the volume. Volume equals A times L. And recall what half Fx gives you. So area is half Fx gives you the energy stored, divided by AL gives you the volume. So energy per unit volume is quantity we call energy density. So the area under stress strain graph gives you energy density. And if there is a reverse question where they ask you how can you calculate the energy, what you do is calculate the area and multiply it with the volume of the sample. One thing I forgot to mention, when it comes to springs, doesn't have to be parallel or series. There are three equations that you have to remember for energy stored or the work done in stretching a spring. One is E equals to half Fx, the one we just saw. The other one is E equals half kx squared, and the third one is E equals f squared by k. So this one is not very common, but I have seen several questions that you have to use only this one. Oh, half f squared by k, my bad. Half f squared by k to calculate the energy stored. And now, just some final suggestions from me. Do not rely only on the predictions. Use this video as a stepping stone. Use this video as a starting point. Make sure this is not what you end your revision with. You just start your revision with this and you just go all in. Review the fact sheet, very important. I have given the link in the description. Memorize the definition sheet. I can promise you, you'll get some definitions from the definition sheet. And my personal request to all of you is do not start from section A. Always start with section B because there is a time constraint. If you start with section A, you might lose a lot of time solving unimportant questions. And even if you get all of these right, you only end up with 10 marks, whereas section B contains most of the marks. Do not forget the units in your answers and give units for the interim calculations. Maintain the SF rule as a significant figure. Never ever give your answers to less than two significant figures. And if it's a show that question, the rule is give your answer to at least one significant figure higher than the show that value. Review the full syllabus revision video, that will be really helpful. And review the full paper solutions. I have some full paper, for example, one of the most recent ones would be May 25. Okay, that's available on my channel. Just see how I encounter and approach every single question in a whole syllabus, whole paper solution video, and solve some papers yourself. Just looking at the videos is not going to cut it. I repeat, please make sure you solve some papers, right? This is really, really, really important. And good luck with your exam tomorrow. Let me know how the exam goes and if this video helps. I'll be waiting for you in the comment section. Thanks for watching.